morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. In the last lecture, I was discussing about the different processes by which we can remove the hardness from water. The first method that I had taken was the process using zeolites. Zeolites, which are generally defined or they are represented as Na2Ze, where the sodium ions are labile or they are loosely bonded to the main zeolite structure, and they are able to exchange the hardness causing cations, specifically calcium, magnesium and other heavy metal cations with sodium ions which are present in zeolites. So, in the last lecture I had explained the complete process. Today I will be taking its numericals. How can we calculate the hardness of water using zeolites? So, the first numerical that I had taken is the hardness of 1 lakh liters of water was completely removed by passing through a zeolite softener. That is the process that I had explained earlier. I had now in the numerical I am passing hard water, and the quantity of hard water that I am passing through the zeolite is 1 lakh liters. So, my numerical says the hardness of 1 lakh liters of water was completely removed by passing through a zeolite softener. So, when I had passed 1 lakh liter of water through that zeolite softener, then this softener was not able to further exchange the cations with sodium ion. That means all its pores became clogged with calcium and magnesium ions, and the efficiency of zeolite softener was reduced. The softener then required 400 liters of NaCl. So, for the regeneration of the zeolite softener, I had to pass 400 liters of NaCl solution, brine solution, which contained 100 gram per liter of dissolved NaCl for regeneration. So, per liter I had dissolved 100 grams of NaCl, and such NaCl I had passed around 400 liters, so that my zeolite softener can be regenerated. Now, I have to calculate the hardness of water. How hard was my water? That means I had to calculate the calcium carbonate equivalence. In terms of calcium carbonate equivalence, how much hardness was present in water. Now, starting with the solution, the total amount of NaCl required for regeneration, as I have already said, that per liter I had dissolved 100 grams and I had passed 400 liters of NaCl. So, 400 liters of NaCl will contain how much solid NaCl? It is going to contain 100 grams multiplied by 400 liters is equal to 40,000 grams of NaCl. Now, 58.5 gram of NaCl, this is the molecular weight, is equal to 50 gram of calcium carbonate. This is the equivalent weight of NaCl, molecular weight and equivalent weight is same, and this is the equivalent weight of calcium carbonate, because the N factor is 2, so equivalent weight is 50. Therefore, 40,000 grams into 10 to the power 3, we are going to do the calculation in milligram, therefore I am multiplying by 10 to the power 3. So, 40,000 into 10 to the power 3 milligram of NaCl will be equivalent to how many calcium carbonate equivalents? It will be equal to 40,000 into 10 to the power 3 multiplied by 50 divided by 58.5 calcium carbonate equivalents of NaCl. So, I am converting the NaCl into calcium carbonate equivalents. This is the result that I am getting. Now, the total volume of water that I had passed is 1 lakh liters. Now, this is the total hardness produced by the water, and how much water? It is 1 lakh liter of hard water. So, 1 lakh liter of hard water produces this much amount of hardness. So, 1 liter of hard water will produce how much hardness? So, here hardness of water is equal to calcium carbonate equivalence of NaCl divided by the hardness. So, the hardness of water will be equal to 341,880,341 divided by 1 lakh liters of water. So, this is the hardness, 341.88 is milligram per liter is the hardness present in the water that I had passed through zeolite. And why I am equating this much? Because this hardness was accumulated in the zeolite and then I required NaCl to remove this hardness from the zeolite material. Coming to the next numerical. Now, an exhausted zeolite softener was regenerated by passing 150 liters of NaCl solution having strength of 150 gram per liter of NaCl. If hardness of water is 600 ppm 600 milligrams per liter, calculate the total volume of water softened by this softener. How much water I had passed through this zeolite? I had to calculate the volume. So, again the total NaCl required for the regeneration of the zeolite is how much NaCl is present in per liter and how much liters of NaCl that I have used. So, by multiplying these two values, I am going to get how much NaCl I had dissolved to make the brine solution. So, it is 22,500 grams of NaCl had been dissolved. Now, again 58.5 gram of NaCl is equivalent to 50 gram of calcium carbonate. So, 22,500 multiplied by 100 milligram of NaCl will be equivalent to 22,500 into 1000 divided by 58.5 multiplied by 50 calcium carbonate equivalents. So, calcium carbonate equivalence of NaCl will come out to be this much. So, this is the total hardness and I know hardness per liter. If I divide these two quantities, the total hardness divided by hardness which is present in 1 liter of water, I am going to get the total volume of water which I had passed through the zeolite softener. So, the volume of water is equal to calcium carbonate equivalence of NaCl divided by the hardness. So, on dividing these two, I get the volume of water as 320.51.2 liters of hard water has been passed through the zeolite softener. Now, coming next to the second process, that is the ion exchange process, which is also known as deionization or demineralization process. Because after passing hard water through this process, there will be no ions present in water, therefore deionized water will be produced, and since there are no minerals also present in water, therefore this water is also known as demineralized water and the process therefore is known as demineralization. So, ion exchange process. Now, the ion exchange resin is the most modern method for softening of hard water. By using this method, almost all salts can be removed from hard water and the hard water obtained is as good as distilled water, because by this process I am going to remove all the different ions which are present in the water. The cation exchangers, the material that I am going to use in this process, they are of two types. The types anionic and cationic exchangers. Now, these anionic and cationic exchanges, because there are two types of ions which are present in water. The two types of ions that are present in water, suppose water contains calcium chloride. So, the two different ions which are going to be present in water are the calcium ions, chloride ion. That means both cations and anions are going to be present in water. So, the exchangers that I am going to use in this method are of two types: anionic to remove the anions in water and cationic exchangers to remove the cations in water. So, both of these whether anionic or cationic exchangers, they are copolymers of styrene and divinyl benzene. That is, they are long chain organic polymers with microporous structure. So, polymers is the base and they contain different functional groups which have the ability to exchange their cations or their anions with the cations and anions which are present in water. Now, coming first to the cation exchange resins. Now, these cation exchange resins, they contain acidic functional groups. Acidic functional groups like carboxylic acid, like sulfonic acid, COH, SO3H, which are capable of exchanging their H plus with the other cations in water, and they are represented as R minus H plus. Similarly, anion exchange resins, these resins, they contain amino or quaternary ammonium or quaternary phosphonium or tertiary sulfonium groups, and when they are treated with NaOH solution, they become capable of exchanging their OH ions with the anions in water, and therefore they are called anion exchange resins, and they are represented as R plus OH minus. Now, this is the process for the ion exchangers. Now, what I do here, I pass impure water. I take hard water containing different salts which produce hardness in water. For example, I am going to take again the example of calcium chloride. Suppose my hard water contains calcium chloride. This is the impurity which is present in water. Now, I pass this impure water first through cation exchanger. When I am going to pass through this water through cation exchanger, the different functional groups which are present in the cation exchanger. Here you can see this is the polymeric chain and these are the different functional groups. This is the sulfonic acid cation exchange resin, and these are the different polymer chain, the base chain which is present, and the exchange when hard water pass through this microporous structure. Here these functional groups, they are going to exchange their H plus with cations in water. What will happen when my hard water will pass through containing calcium chloride? H plus will move out of the system, and here calcium ions is going to get fixed. So, calcium ion is going to get fixed, and similar amount 2 hydrogen ions, they are going to move out of the system. So, here when I pass this impure water through the cation exchanger, calcium ion is going to fix here, get fixed, and chloride ions along with H plus ions, they are going to move out from the cation exchange resin. So, the water now contain H plus and the anions which are present in water, and then it passes through the anion exchanger. Now, so the water is going to pass here. Now, this water will contain H plus and different anions, whether chlorides or sulfates. So, different anions are going to be present. All other cations, whether calcium, magnesium or heavy metals, they are going to get fixed here. Now, this water will be passed through anion exchange resin. So, when it passes through anion exchange resin, similar process, they contain quaternary ammonium. Here you can see the example quaternary ammonium salts are present, and they are capable of exchanging their OH with anions in water. What happens? This OH moves into water, and the chloride ions which were present here, which passes through the anion exchanger, they get fixed here. So, now here when the water containing H plus and Cl minus pass through this anion exchanger, this Cl takes the place of OH minus and OH minus combines with H plus to form pure water, and this pure water moves out from the anion exchanger. Since there are certain dissolved gases also, they also move along with the pure water. So, this water is soft water containing only H plus and OH minus ions and different gases. So, these gases, they are passed through the steam jacket and finally through the degasifier. They are passed to remove the dissolved gases, and the water which is coming out from the system now is the demineralized water. So, it is the demineralized water which is passing out from the system. Now, after certain amount of water has been passed through these cation or anion exchangers, again their capability for exchanging the cations and anions will reduce. So, to regenerate them so that we can again use them properly, we pass dilute acid for the regeneration of cation exchangers, and these anion exchangers, they are passed, dilute alkalis are used for the regeneration of the anion exchangers. So, different reactions are going to take place. I am going to show you in the next slides, and again H plus and OH minus, they are going to get restored in their original places, so that hard water can once again pass through the system. So, this is the polymeric chain, the basic structure containing functional groups. Now, the process I have already explained, but still the hard water is passed first through cation exchange column, which removes all the cations like calcium, magnesium ions from it, and the equivalent amount of H plus ions, they are released from this column to water. So, these are the different reactions which are going to take place. The cation exchanger, it is going to get bind with the hardness causing cations, they are going to get fixed into the cation exchangers, and equivalent amount of H plus will be released into the water. Similarly, after the cation exchange column, this hard water is passed through anion exchange column, which removes all the anions, whether sulphate or chloride anions, which are present in the water, and equivalent amount of OH minus ions, they are released from this column to water. So, the different reactions which are taking place, this is the hydroxyl form of the anion exchangers. So, they react or they exchange the anions get fixed in the anion exchange column, and equivalent amount of OH minus is released in water. The passing water contains. Now, the passing water coming out of both the cation and the anion exchanger, their H plus and OH ions, they get combined to produce water molecules, and this water coming out from the exchanger is deionized or demineralized water. Now, coming to the regeneration process, how do we regenerate? When the capacities of cation and anion exchangers to exchange H plus and OH minus is lost, then they are said to be exhausted. When they are not in a condition to exchange their H plus and OH minus, then they are said to be exhausted. Therefore, the exhausted cation exchange column, it is regenerated by passing through a dilute solution of acid. The acid can be either HCl or H2SO4, and the regeneration process, it is represented as, suppose calcium was fixed in the cation exchangers. So, acid gives out H plus. Now, this H plus, it moves out the calcium from the system and it occupies its original position. Similarly, the exhausted anion exchange column, it is regenerated by passing a solution of dilute NaOH, and the reaction is dilute NaOH will give you OH minus. Now this OH minus gets incorporated back into the anion exchange resin and the sulfate ions move out from the system, they are removed through the washings. Now the process, this process is always run in this order only, that first the hard water is passed through cation exchanger, only then it will pass through the anion exchanger. Why it is so? Because when we pass, the reverse of the process is not possible. What I mean to say, that we cannot pass water first through an anion exchanger and then through cation exchanger. Why? Because when we pass this impure water through the cation exchanger, this water coming out, it contain H plus and Cl minus or H plus and sulfate ions. If you see clearly, these are the formation of acids. I am here showing the formation of acids HCl and H2SO4. So dilute acids are formed. Now these dilute acids, when they pass through anion exchangers, they do not affect much the anion exchanger bed. Anion exchanger bed is not affected by these dilute acids. But if I take the reverse process, first I pass my water through the anion exchanger and then through cation exchanger, then my water coming out first from the anion exchanger will contain hydroxides of calcium, magnesium, heavy metals as well as sodium. Sodium, it does not produces hardness, but it is present in water. So this is going to result in the formation of caustic element, that is NaOH. So NaOH is going to be formed, and this NaOH, it has the capability for destroying the cation exchanger. It is much stronger than the dilute acids, so it can destroy the cation exchanger. Therefore, the reverse process is not done. The sequence always remains. First the hard water is passed through cation exchanger and then through anion exchanger. So this is the regeneration. Coming to the advantages. Now this process is used to soften highly acidic or alkaline water, and water of very low hardness is produced. Less than 2 ppm hardness is left, that is the residual hardness. And the disadvantages, the equipment is costly. Obviously we have to use both cation exchangers as well as anion exchangers, so the setup is costly. And if water is turbid, the output of the process gets reduced, because turbidity again gets settled on the beds, whether the cation exchanger bed or the anion exchanger bed, hence the output of the process get reduced. Now next is the desalination of brackish water. Now what do we mean by brackish water? If water contains high concentration of dissolved solids, so high that it gives a very peculiar taste to the water, salty taste to the water, such water is known as brackish water. And this brackish water is unfit for domestic and industrial purposes. So we have to remove the salts before we can use such water for either domestic or industrial purposes. And the process of removing salts is known as desalination of brackish water. Now there are different methods for the desalination of brackish water, but I am going to concentrate on one method, that is reverse osmosis, because distillation is also one process, freezing is another process, but I am going to concentrate only on the subject, that is, and we have only one process going to study in detail, that is the reverse osmosis. Now, reverse osmosis is totally different kind of process where two different solutions having different concentration of salts, these two water, they are separated by a semi-permeable membrane, and when the water flows from its low concentration solution to the high concentration solution, so that the concentration on both the sides becomes same, this process is a natural process and it is known as osmosis. But reverse osmosis is totally opposite of osmosis, that is, if we apply pressure on the concentrated side, then the solvent, it moves from the highly concentrated solution to the low concentrated solution, so that the salts, they are left on one side and we get fresh water on the other side with limited hardness. So, reverse osmosis is not a natural process, therefore, we have to apply a pressure such that the water from the concentrated solution side, where the concentration of water is low, solvent is low, but solution is concentrated, it passes from that side to the side where the concentration of solvent is high or where the solution concentration is less. So, this process is known as reverse osmosis, and the semi-permeable membranes that we generally use, they are cellulose acetate, they are polymeric membranes. It can be cellulose acetate, it can be polymethyl acrylate, or they can be polyamide polymers. Now, in order to reverse this osmotic flow of water, external pressure greater than the osmotic pressure of both solutions has to be applied. This additional external pressure, it enables the dissolved salts to be separated from the water, and therefore, this phenomenon is defined as reverse osmosis. Now, this reverse osmosis, it is generally divided into three categories. First category is the high pressure reverse osmosis, where we use the pressure of 5 to 10 megapascal as in the seawater desalination. Then the low pressure reverse osmosis, where the pressure is around 2 to 5 megapascal as in the brackish water desalination, and nanofiltration, where the pressure is around 0.3 to 2 megapascal as in the softening of drinking water. Now, the membrane process used in the water purification system has been of much use nowadays. Generally, every household has a RO at home. Now, electrodialysis and reverse osmosis, they are the part of the membrane process. In osmosis, if a semi-permeable membrane separates two solutions, solvent from the lower concentration passes through the higher concentration to equalize the concentration of both. But in the reverse osmosis, the pressure higher than osmotic pressure is applied on the higher concentration side, so that the path of the solvent is reversed, that is from a higher concentration to a lower concentration. Coming to the applications, now this method is applicable mainly for the desalination of seawater. Now, seawater and pure water, they are separated by a semi-permeable membrane made up of cellulose acetate fitted on both sides of a perforated tube. Now, the inventions are in progress to search for better membranes. Polymethyl methacrylate and polyamides have been proved to be better membranes. Coming to the advantages, the process is very easy and we can use or we can prepare pure water. It also removes the ionic and the non-ionic substances in the water, and this process can also remove the colloidal particles. The life of the membrane is nearly 2 years, and therefore, it should be replaced after this period. By this process, seawater is made to fit for drinking purposes. Obtained after being treated by this process, it is used in boilers. And again, this water, RO water, treated RO water, they can be used in cosmetic industries also. Thank you.